Hello everybody, this is Dr. Christopher White, and today we're going to start focusing on the formation of the continents with a special focus on North America. So obviously we're going to start at the beginning, so we're going to begin in the Precambrian, and today's lecture is going to be focusing on the Hadean and the Archean, the first two of the three parts of the Precambrian. So geologic time primarily focuses on periods during which we have easily identifiable life in the form of fossils. So if you remember, when packages of rocks are split up into systems, you also need to remember that systems were, of course, are now called periods. Those systems are essentially defined by the first and last appearances of certain key fossils. So the problem is that before 542 million years, that's the Precambrian Proterozoic boundary, the rocks that form before 542 million years, so they're older than 542 million years, while those rocks do not have fossils in them, in the kind of sense that we would think of them macrofossils. So that's a bit of a problem. Essentially, that means that because the Earth is about 4.6 billion years old, it means there is essentially 4 billion years worth of time in the form of rock, which is not split up. You know, that 4 billion years accounts for 88% of all geologic time on Earth, so, you know, that's a pretty significant chunk of time. So if we look at the Precambrian, we can see it makes up these three rather large segments here. So we have the Hadean, which is about 17.4% of all geologic time, the Archean, 28.3%, and the Proterozoic, 42.6%. So we can, and then compare it to the other periods of Earth history, which you can see, account for approximately 1% of geologic time each. So we can quite clearly see that the Precambrian makes up a very significant portion of all geologic time on Earth. So up until 1982, the term Precambrian was used to describe any rock that fell below Cambrian age rocks. Essentially, it was just a bucket term. As soon as you knew the rock was older than the Cambrian, you would say, right, Precambrian, done. So that's a lot of time, obviously, as we were discussing. But the problem is, of course, without fossils, dividing things up was very, very difficult. So, the other thing that would be helpful is obvious marker horizons, but of course, there weren't those either. So, in 1982, the Precambrian was split up into three eons. The Hadean, which goes from about 4.6 to 4 billion years. The Archean, 4 billion years to 2.5 billion years. And the Proterozoic, 2.5 to 541 million years. So, essentially, you're thinking, well, why were those boundaries selected? The answer is, on the whole, they're actually relatively arbitrary. So, as I said, because there's a lack of dating evidence that occurs on a large global scale, selecting the events that can represent the changes that allow us to define these boundaries is proven rather difficult. Because once again, we want to change in fossils, we want to change in rock type, we want some kind of very obvious thing to happen that tells us we're moving from moving across one boundary and into a new period, era, or eon. But we don't have that in the Archean. And so what's happened is, and if you just look at the diagram here, what you'll notice is 4 billion years to 3.6, 3.6 to 3.2, 3.2 to 2.8. Essentially, they're just dropping down by 400 million years each time. And you can see that throughout the Proterozoic as well. So essentially what we're looking at here is they've just split up the Precambrian based on arbitrary numbers that don't really have too many, don't really have any kind of evidence to anchor them. They're just, boundaries that were picked because they're nice round numbers. That's it. So an attempt was made in 2012 to anchor the boundaries, to actually mark these boundaries out based on things that could be measured in the rock record. So the new boundaries have not been accepted yet. So the boundaries differ from these ones that you can see marked out in the diagram. So we must remember that during the Precambrian things were rather different. So for a while we didn't have a complete crust. As the Earth's interior was a lot hotter, plate tectonics would have been a lot faster. The oceans were in the process of forming, any time after about 4.4 billion years ago. The Earth's atmosphere evolved from one that was very carbon dioxide rich to one that contained free oxygen. Of course, once there was free oxygen, an ozone layer could develop. Before there was free oxygen, no ozone layer. And of course, we know life didn't appear in, well, we don't know, but we have a pretty good idea that life begins to make an appearance around 3.5 billion years ago, possibly earlier. So as the Precambrian progressed, conditions became increasingly like those today. So, if you jump in a time machine and go back to the Hadean, we would probably be absolutely shocked at what we're seeing. On the other hand, if we took a time machine and went all the way back to the end of the Proterozoic, things would look far more logical to us. All right, so let's start with the Hadean. So, of course, the Hadean was a time when, the Earth was forming from magma ocean, so it's going to be a period where, the tectonics of the Earth are going to be very, very haphazard. So, the Hadean encompasses the period between the formation of the Earth and the start of the Archean. So, it makes up about 600 million years, give or take a little bit. So, the end of the Hadean is marked by the oldest known crust, and that's the Acasta gneiss, which is found in Canada. So the Acasta gneiss is considered to be the first evidence of stable crust. You're thinking, well, why is it the first evidence of stable crust? The answer is it's the first piece of crust that has survived, and therefore, in order to survive for all this time, it has to have been stable. If it was unstable, it would of course have sunk down into the Earth's mantle, into the magma ocean, and it would have been destroyed. So, as we previously discussed, the Earth formed by accretion of material in a circumstellar disk around the juvenile Sun. So, we know that. So, what most people don't know is the Earth actually underwent a second period of accretion. That occurred between about 3.8 and 4.1 billion years ago. And this is called the Late Heavy Bombardment. And essentially it straddles the Late Hadean and into the very, very early Archean. And this is a period where the Earth was bombarded with meteorites and comets. So this period produced a substantial portion of the craters that are visible on the Moon. If we extrapolate based on the size of the Moon and the number of craters on the Moon, it suggests that the Earth would have been hit approximately 22,000 times during this period between 3.8 and 4.1 billion years. So, this approximately 300 million year range. So this bombardment is actually important as it helped to add more sidrophile elements to the mantle and the crust. So if you remember, when the Earth initially formed, we formed the Earth's iron core, and because, sidrophile elements, iron-loving elements, want to go with the iron, well, they all got vacuumed up by this iron core, and they're all trapped down in the Earth's core right now, so we can't get to them. So, so if we want sidrophile elements like, platinum and palladium, the elements like that, well, where would they be? How do we find them now? Well, the answer is they've been added later. The ones that we managed to, mine now are on the whole the result of the addition due to the Late Heavy Bombardment. And so all these meteorites, all these comets that came flying down, well, quite a lot of them carried, platinum and palladium and nickel and cobalt in relatively large quantities, and so that helped to essentially seed the Earth's early crust and the Earth's upper mantle, essentially allowed us to, add new material to that. So there are some sidrophile elements in the upper mantle and in the crust. Now, a lot of the meteorites, a lot of the bodies that hit the Earth during this period would actually have been comets. And comets are very, very water ice rich. So there is a reasonable, it's a very reasonable suggestion that the Earth's early ocean, the formation of the Earth's early oceans may well have been assisted greatly by the addition of all this water coming from outer space in the form of comets. So the Late Heavy Bombardment is very, very important. Number one, it makes the Earth slightly bigger. Number two, it adds sidrophile elements to the upper mantle and the crust. And number three, it provides a lot of water. So why did the Late Heavy Bombardment happen? Well, it could have resulted from a number of factors. Essentially, what you need is some kind of very large event in the solar system that destabilizes the asteroid belt and the Kuiper belt and the Oort cloud that sits at the edge of the solar system. So as you know, the asteroid belt sits between Mars and Jupiter. The Oort cloud and the Kuiper belt essentially sit beyond Pluto. So the Oort cloud and the Kuiper belt is right at the edge. That's mostly made up of comets. Whereas the asteroid belt, as the name suggests, is mostly made up of asteroids, more rocky bodies. So essentially what you need to do is you need to disturb these bodies, and when you disturb them, essentially that's going to agitate the comets, for instance. That's going to make them fall out of their stable orbits, and the gravity of the sun is going to pull them towards the inner solar system. So the question is what kind of event could cause that? Well, typically you need something relatively big to happen. So, the most logical explanation is that Neptune and Uranus, which formed in between Jupiter and Saturn, began migrating out towards their current positions. And as they migrated out, because they're very, very large planets with a lot of gravity, as they moved outwards, they began to essentially, their gravity at least, began to disturb the orbits of comets and other bodies, in the Kuiper Belt and the Oort cloud. There's another possibility that Jupiter began to migrate in towards the Sun a little bit. That would have disturbed the orbits of asteroids within the asteroid belt. There's also the possibility that Mars passed through the asteroid belt. Mars was actually on the outside the asteroid belt, and it migrated inwards towards its current position. If it had passed through the asteroid belt, that would have disturbed asteroids and possibly thrown them into the inner solar system towards Earth. There's been another model that suggests maybe there was actually a fifth planet within the inner solar system, and that actually got thrown out of the inner solar system. And as that planet was thrown out of the inner solar system, it disturbed the asteroid belt once again, causing asteroids to come in towards the inner planets. And there's also the possibility that Jupiter and Saturn could have formed what's referred to as an orbital resonance. That's when they repeatedly line up, and every time they line up, essentially their gravity combines, and that will disturb the orbits of comets and asteroids. And then of course it could have just been the formation of Uranus and Neptune between Jupiter and Saturn in the first place. That could have disturbed the gravity in the solar system enough to have made the orbits of these comets and asteroids unstable. So there's lots and lots of possible reasons as to why this happens, and of course the problem is no one was around at the time, so we can't be 100% sure. What we do know though is it happened. It added water, it added signified elements to the Earth, to the Earth's upper mantle and crust, and it will also have helped to add material to the Earth, making it larger. So currently debate rages about whether the heat produced by this late heavy bombardment could have been high enough to fully or partially melt the Earth's crust. You have to remember, the Earth's crust was being absolutely pummeled during this period. And, and I'm sure, as just think of a nuclear explosion. So I'm sure we've all seen film of a nuclear bomb going off. That's a pretty powerful explosion. When a very, very large meteorite or a very, very large comet hit the Earth, that would be nothing. A nuclear explosion would be nothing compared to that kind of impact and the amount of energy released. Now imagine that happening 22,000 times. There's a very realistic possibility that the amount of heat produced by those impacts would have been sufficient to melt the Earth's crust. So it had been assumed that the Earth's surface was molten until about 3.8 billion years ago. Now, that was a bit of a problem. Why did we think that? Well, the oldest crust that we have, the oldest, really, really big piece of crust, dates to around 3.8 billion years ago. So people assumed that, well, the first major pieces of crust obviously didn't form until 3.8 billion years ago. The problem is that when you look at the Earth and calculate the way the magma ocean would have cooled down, well, the data strongly suggests that the Earth should have actually had a crust that was older than 3.8 billion years. So there should have been a crust that formed a long way before 3.8 billion years. So obviously the problem then becomes is, where is this crust? What happened to it? So the evidence of this early crust is backed up by the presence of the Jack Hills zircons from Australia. So it's a group of zircon crystals, and they've been dated, and a few of them dated to 4.4 billion years old. Now this dates to around the time when the Earth's first crust should have been forming. And the most important thing is we know they have to have been part of the crust because the zircon crystals that we measured are detrital. So they've been weathered out of a pre-existing rock. And obviously if that rock that they've been weathered out of essentially has to be exposed to the atmosphere, and if it's exposed to the atmosphere, it has to be part of the crust. So we know that the rock that provided these very, very old zircons must have been a crustal rock. So the Jack Hill zircons tells us that yes, there was a very, very early crust, and it was actually formed, all the way back to 4.4 billion years. So then you have to say, right, where is this crust? Well, we have a small part of something that might be associated with it in the form of the acastanite, but that's a tiny piece of rock. So the question becomes, what happened to the rest? And the most reasonable explanation is that, yes, it was actually melted by the late heavy bombardment. So this late heavy bombardment between 4.1 and 3.8 billion years ago, hit the Earth so hard with so much energy that all of these impacts caused the Earth's surface temperature to rise, and the crust melted and has been destroyed. Eventually things cooled back down again, and we started to see the formation of a solid, stable crust again by somewhere in the region of about 3.9, 3.8 billion years ago. So during the Hadean and the Archean, the heat of accretion had less time to dissipate, and there were higher concentrations of radioactive isotopes in the mantle. So that meant the Earth's interior was considerably hotter than it is now. So if you remember, obviously we remember what radioactive isotopes are, but if you remember, the heat of accretion is the energy essentially that was put into the Earth every time an impact occurred as the Earth was building itself through accretion. So every time the Earth got hit by something, it would put a little bit of heat energy into the Earth. Now you have to remember, the Earth was formed by literally hundreds of thousands, millions, maybe even trillions of little impacts all coming together. So that's a lot of energy being added to the Earth, and that heat energy produced by all those little impacts essentially is referred to as the heat of accretion. So during the Hadean and Archean, there was lots more heat energy in the form of the heat of accretion, and lots more heat energy in the form of radioactive decay occurring in the mantle during that time. Now this means that as the Earth's mantle was a lot hotter, it meant the Earth's mantle was a lot easier to melt. And this meant that there was lots of volcanism, especially during the early to mid-Hadean. So you have to remember there was very little water to help lubricate processes like plate tectonics. So this, is rather important. So water helps to make plate tectonics happen more easily. If you're in an environment where there is very little water, like the early Hadean, it makes it very difficult for plate tectonics to happen. And so that means the crust that, the forms would naturally have only been able to essentially break up and recycle itself through rifting and subsidence, rather than the process of, subduction, for instance, which is a relatively controlled process. So it would have meant that in the early to mid-Hadean, the crust would have been very, very unstable. The crust would have been covered in volcanoes. There would have been lots of rifting going on, and lots of lava pouring out onto the surface of the Earth through huge cracks. It would have been a very, volcanic, very, very explosive time in Earth history. So all these volcanoes, all these eruptions, will have released very substantial quantities of gases into the Earth's atmosphere, and essentially that's where our atmosphere came from. So the atmosphere would have been rich in gases like carbon dioxide, hydrogen sulfide, methane, and water vapor that were being released by the volcanoes. So we are certain that the Earth's surface had stabilized sufficiently by about 4 to 3.8 billion years to allow a solid, continuous crust to form. Now, we know this because we have pieces of crust that date back to around this period. So we know there was a crust. Now, the lower end of this, of course, if we just remember from a few slides ago, that was when the Earth was, of course, being pummeled during this late heavy bombardment. So this very old crust isn't particularly common. We have material that sits more at this end of the scale, but we know with relative certainty there would have been a crust. So it's difficult to say when the first crust formed. However, as I also discussed a couple of slides ago, we know that there's a very good chance we had a crust of some type by 4.4 billion years, so approximately 150 million years after the Earth formed. As we also discussed, that early crust was probably destroyed as part of the late heavy bombardment. Whether that early crust was continuous and how strong it was is obviously very, very debatable, because we don't really have any samples of it. Excuse me. So as we already discussed, we know this early crust must have existed because we have these detrital zircons from sedimentary rocks in the Jack Hills area of Australia, and they date to 4.4 billion years. And as also discussed, as the zircon grains are detrital, we know they must have been weathered from a pre-existing rock, and if they're being weathered from a pre-existing rock, they must have been exposed to the atmosphere, and therefore that rock must have been part of a crust. So we should also not forget the Acasta gneiss. This is the photograph of the Acasta gneiss here. That dates to 4.2 billion years. And the Isha Greenstone belt in Greenland, that dates to 3.8 billion years. Now, in the case of the Acasta gneiss, it's an absolutely tiny area of rock. It's a very, very small piece of crust. So, it's literally the tiniest remnant of crust that's managed to make it from this very, very early period in Earth's history. In the case of the Isha Greenstone belt, it's a lot larger, and so we know with relative certainty this represents a big chunk of stable crust that was around 3.8 billion years ago. So we know we definitely have to have had a solid stable crust 3.8 billion years ago. And the Archean Earth also says, yes, there was definitely a solid crust at 4.2 billion years ago. So we know we had to have a solid crust definitely, essentially, during that period. That's where we know the first super stable crust has to have formed. Of course, the other thing is that both the Archean Earth and the Issuer Greenstone Belt, well, they're both metamorphic rocks. So that means that whatever rocks formed these two bodies of metamorphic rock, well, the protoliths have to have been considerably older, and therefore they have to predate them. So, the Issuer Greenstone Belt might date to 3.8 billion years, but the rock that actually was metamorphosed to make the Issuer Greenstone Belt obviously has to be older than 3.8 billion years. So that's another piece of information that we need to keep in mind here. So both of these locations definitely tell us we had a stable crust somewhere in the region of about 4.2 to 3.8 billion years ago. But once again, as we discussed, this crust was being pummeled by the late heavy bombardment, and a lot of it would have been melted and destroyed. So what was the Earth's very early crust like? Well, let's discuss that in a second, because it's been 20 minutes. So this would be a good time to pause the presentation, get up, have a walk around, get a glass of water, and come back in a couple of minutes, please. Okay, so we know the Earth's first crust must have crystallized directly from the magma ocean. So if you remember Bowen's reaction series, when we have a body of magma cooling, the first minerals that will crystallize will be very, very high temperature minerals, and in the case of the Earth's magma ocean, those high temperature minerals would have been olivine and pyroxene. And they will have crystallized first, and olivine and pyroxene will have gone to form the Earth's mantle. So after olivine and pyroxene, the third mineral that would have crystallized would have been calcium plagioclase feldspar. Now, this is pretty important. So the magma ocean had a density of about 2.8 grams per centimeter cubed. Okay. Now, in the case of olivine and pyroxene, they have densities of 3.3 and 3.2 grams per centimeter cubed. They weigh more. So when a big crystal of olivine formed, it would naturally sink because it was heavier than the surrounding magma in which it was sitting, or should I say floating. Same with a crystal of pyroxene. So that's how the mantle went and formed. These big crystals of olivine and pyroxene would form, and they would naturally sink through the magma ocean, and eventually they settled out to accumulate over time and form the Earth's mantle. Now, in the case of calcium-rich plagioclase feldspar, otherwise known as anorthite, the situation is slightly different. Anorthite has a density of 2.73 grams per centimeter cubed. So it doesn't sink, it floats. So this means that once crystals of this very calcium-rich plagioclase feldspar started forming, they would naturally begin to float on the surface of the magma ocean, where they would eventually begin to lock themselves together, and they would form the Earth's first crust. And the Earth's first crust would probably have been a type of rock which is called a anorthosite. That's a rock that's made up mostly of calcium-rich plagioclase feldspar. It's actually a mafic igneous rock. And if you actually look at the moon, you can see that the moon has large areas which are essentially white to light grey in colour. Those are referred to as the highlands, and they are made up of anorthosite. So this prediction that the Earth's early crust would have been made from anorthite isn't just a guess. We actually have our partner satellite that gives us a good indication that it's a very realistic model. So we also know that as the Earth's mantle would have been a lot hotter, it would have been convecting very, very quickly. So this means there would have been lots of mantle upwelling and lots of mantle downwelling. So it means the mantle would have been convecting very, very fast, would have been very, very unstable, and so it means any crust that was sitting on top of this rapidly convecting mantle would also have been rather unstable. And so this would have produced very, very chaotic tectonics, possibly even very limited subduction. But most of what will have happened will have just been the crust being ripped to pieces and rifting, and magma pouring up from any resulting cracks. So if subduction did take place, well, any subduction that occurred would obviously have resulted in rocks being pushed down into the mantle, where they would have started to melt. And the partial melting of these rocks would probably have produced magmas that had an approximately felsic to intermediate to maybe mafic composition. And these magmas would have excuse me, These magmas would have risen up through the crust, where they would have erupted on the Earth's surface in the form of volcanoes, volcanic arcs, and of course that would be the start of the continental crust, because these volcanic arcs would have mostly been felsic to intermediate in composition, and they are going to start combining to form the continental crust. So erosion of these very, very early arcs would also produce sediments that would contain feldspar and quartz, and of course zircon. So this is possibly where the Jack Hill zircon is coming from, one of these very, very early volcanic arcs. So as with the moon, the Earth's early crust would have rifted because the mantle below would have been very unstable, and when it rifted it would have allowed the mantle underneath to melt. And as the mantle melts underneath, it would have produced a mafic magma that would have risen up, erupted onto the Earth's surface, where it would have cooled to have formed basalts. So as we can see here, here's a picture of the moon. We have the light grey-white areas. These are the highlands made of anorthosite. And over here we have the darker areas. These are referred to as the Mars, otherwise known as the lunar basalts. They were essentially produced by rift volcanism, so there were cracks in the surface of the moon, and basalt came pouring out onto the surface. And the thing is these very basalt-dominated areas, well, basalt is naturally very heavy. So it pulls down the Earth's, well, it pulls down the crust of the moon here, and it would have done the same thing on the Earth, that the weight of all this basalt would have naturally pulled down the Earth's crust, creating topographic lows that would eventually start to fill with water. So the eruption of these rift basalts essentially creates, topographic depressions, which will essentially be the focus of the first, bodies of water that begin to form on the surface of the Earth. So the very early Earth would probably have looked something like this, but with, because there was this chaotic, plate tectonics going on, there would also have been volcanoes, large cracks on the surface with magma pouring out. Okay, so let's think about the formation of the oceans. So about 150 to 500 million years after the Earth formed, the surface of the Earth and its atmosphere would have cooled to around 25 to 100 degrees Celsius. So we're at the point where liquid water can persist, and as such, precipitation would have begun. So we know that some surface water must have existed during a period between 4.3 and 4 billion years ago, because we can actually see that in the oxygen isotope ratios of zircons. So once again, the Jack Hills area provides a lot of zircons, very, very old zircons. Now, the most important ones are the ones that got dated to 4.4 billion years ago. They tell us when the Earth's first crust formed. That's very important information. But some of them also showed us other things. So when we analysed those zircons and we looked at the oxygen isotopes, so we looked at oxygen 18 and oxygen 16, we realised that something interesting had happened. The amount of oxygen 18 in these zircon crystals was higher than we would have expected. Now, typically when we find a crystal that has a higher oxygen 18 concentration than we would expect, what's often happened is that crystal has come into contact with surface water, i.e. cold water from the surface of the Earth. So this increased amount of oxygen 18 is a strong indicator that these zircons from about 4.3 to 4 billion years ago have come in contact with cold water from the surface of the Earth, and therefore that would very strongly suggest there were some kind of bodies of liquid water on the surface of the Earth during this period. So it would suggest that the first lakes and oceans were probably beginning to form anywhere up to 4.3 billion years ago. So this early water would probably have been slightly acidic, because the water would likely have reacted with hydrogen sulfide in the atmosphere, which has been put into the atmosphere from volcanoes, and that would have produced very small amounts of sulfuric acid, and so the pH of the early oceans and lakes on the surface of the Earth would probably have been slightly towards the acidic end of the scale. Now, the one thing we don't know is we don't know how extensive these early bodies of water would have been. Essentially, it's anyone's guess. Some people say they would have been isolated little lakes, and some people suggest that during this period there's the possibility the Earth could have nearly been completely covered in water. So it's best guess, I'm afraid, when it comes to that particular problem. So the very early Earth has a bit of a problem, and this problem is referred to as the faint young sun paradox. So when the Earth was young, the Sun would have been about 25 to 30% less luminous than it is now, so the Earth would have received less sunlight. So this means the Earth's surface temperature would have been about 25 degrees Celsius lower than present. So that would have put the temperature on the surface of the Earth at pretty much zero, or below zero. So if, as some data suggests, the Earth's surface cooled quickly, and water began to collect in these topographic lows, forming lakes and oceans, then any surface water may well have been frozen. So it suggests that maybe during this early period of Earth history, the Earth would have been essentially a giant ice cube. However, as we just discussed, these zircon crystals from 4.3 to 4 billion years ago show very strong indications of having formed, or at least having come in contact with cold, liquid water. And so how do we explain this? How do we explain the fact that one bit of evidence, well, one calculation suggests that the Earth should be an ice cube, whilst the evidence we have suggests that no, there was cold liquid water moving around on the surface of the Earth, which should, based on the modelling, have been frozen. So the ability of any surface water to persist, let's try that again. The ability of any surface water present to remain liquid could be explained by one of four possibilities. The first one is the Earth's atmosphere. So we had a stronger greenhouse effect. So the atmosphere of the early Earth would have been very carbon dioxide rich, there would have been some methane, and there would have been lots of water vapour. These three gases are all greenhouse gases. You wouldn't think water vapour is a greenhouse gas, but it is. It's a very, very weak greenhouse gas. So the fact that the Earth's early atmosphere would have been very, very rich, especially in carbon dioxide, may well have created a much, much stronger greenhouse effect than we have now. That would have trapped more of the juvenile sun's solar radiation, and therefore it would have helped to keep the Earth's surface temperature hot enough to support liquid water. So that's possibility number one. Possibility number two is radiogenic heat. So as we've already discussed, the Earth's mantle during this period was full of radioactive isotopes, a lot more than we have now. And those radioactive isotopes were decaying. As they decay, they produce lots of heat energy, and a lot of that heat energy would conduct through the Earth's crust. So that means the Earth's crust during this early period would probably have been a lot warmer than it is now, because there was more heat energy conducting from the mantle through the crust and essentially onto the surface of the Earth. So that's another reason why the Earth's surface could possibly have been capable of supporting liquid water when, in theory, it shouldn't have been able to. We also have the possibility of tidal heating. So tidal heating is the result of the gravitational pull between two bodies. So in our case, it's going to be between the Earth and the Moon. Now, during this very early period, the Moon would actually have been a lot closer to the Earth. It's actually been drifting away from us very, very slowly. So this means that the Moon's gravity would have been a lot stronger. So essentially the Moon would constantly have been tugging, pulling the the mass of the Earth towards it. Okay? So although when you think about the Earth and the Moon, you only really think about how the Earth holds the Moon in its orbit. You think about the Earth's gravity being important, but the Moon has gravity of its own, and the Moon's gravity is going to tug on the Earth. And so what happens is whichever side of the Earth has the Moon on it, well, the Moon is going to pull the mass of the Earth, including the mass of the Earth's interior, towards it ever so slightly. And the Moon is, of course, constantly orbiting around the Earth. So it's constantly moving from one side of the Earth to the other, pulling the Earth's interior one way, then pulling the Earth's interior the other way, then another way, then another way. So it's constantly stretching, and as the Moon moves around, Moon orbits around, one area gets stretched, then the Moon keeps going, that area then relaxes, and another area is getting stretched, and that relaxes. And the fact you have all this stretching and relaxation essentially causes the Earth's interior to begin to heat up due to frictional heating. Just a bit, the same kind of process that makes your hands warm when you rub them together quite vigorously. So tidal heating would also have played a part. It would have made the Earth's interior warmer, which then would have gone back into all this extra heat that would have been conducting through the Earth's crust, which would have helped to keep the Earth's surface warmer than we would have expected. And then finally, the final possibility is albedo. Essentially, that's a measure of how light or dark the Earth's surface is. So the lighter the Earth's surface is, the more sunlight would be reflected into space, and therefore the more solar energy would be lost, and therefore the colder the surface of the Earth would have been. So what we would really want at this period is we want the Earth's surface to be very, very dark, because that would mean that essentially more solar radiation would be absorbed because the Earth's surface would be dark. That means more of the heat would be retained, and therefore that would mean that the Earth's surface would be warmer than we would have expected. So the first question is, well, what could possibly have, been dark enough to retain large quantities of solar radiation? Well, we've already discussed the Earth's early surface would more than likely have been rather light in colour. So that's not very helpful. That's actually going to be reflecting light back into space. But there is something that would essentially cause the Earth's surface to be considerably darker, and that would be water. If we had large quantities of water on the surface of the Earth during this early period, well, water is actually quite dark, and it's very, very good at absorbing sunlight. It's much better than continental crust. So water can absorb a lot more heat a lot more efficiently, and as such that would have also have helped to keep the Earth's surface temperature higher if we had large quantities of water on the surface of the Earth. So a combination of these four factors, or just one of these factors working on its own, may well have been sufficient to keep the water on the surface of the Earth liquid at a period when in fact the surface of the Earth should have been essentially a giant ice cube. Alright, so that was the Hadean, and to be honest, as you might have noticed, it was, we don't have a lot of very solid information on that time period. A lot of it is based on modelling and prediction. However, once we move into the Archean, things start getting a little bit better, because we actually start having pieces of crust which we can go to and we can look at and we can measure. Now, the Archean accounts for about 32.6% of geologic time, and it goes between 4 billion years ago and 2.5 billion years ago. So Archean age rocks are not uncommon, and outcrops can be found on all continents. Archean rocks do, however, present a bit of a challenge for 3 reasons. Number one, many outcrops have been metamorphosed and have suffered very complex deformation. So if you look at this picture behind us here, you can quite clearly see that those rocks are a bit of a mess. And so from a geologic point of view, they're quite difficult to work with. What you really want is a nice unmetamorphosed, undeformed rock. That would be the perfect situation. What you can quite clearly see from this picture behind is that in the Archean you don't really get that. Another problem with Archean rocks is that most of these rocks are very deeply buried beneath younger rocks, so we can't get to them. And of course, the other problem is that they contain few fossils, and the fossils they do contain are microfossils. And that makes it very, very difficult to allow us to essentially split up the Archean and also to correlate between areas of Archean rock. So Archean rocks are present, but they are challenging to work with. So this brings us on to shields, platforms, and cratons. Cratons can also be referred to as a craton. It depends on how you want to pronounce it. So Precambrian rocks typically form the nucleus of the continent. So for each continent, there's typically a large chunk of Precambrian rock that makes up the core. So along the margins of these Archean cores, or should I say Precambrian cores, rocks have accreted, so stuck on, or sediments have been, that should say, deposited. My apologies for that. And as material sticks onto the side, or sediments are deposited along the margin, obviously the continents have grown larger. Now, areas where the Precambrian crust is exposed so you can walk on it, those areas are referred to as the shield. So in the case of North America, the shield is mostly in the country of Canada, and so it's called the Canadian Shield. There are little bits of Precambrian rock that you can walk around on, if you happen to be in areas like Vermont, New York State, Minnesota, that kind of area. Now, the rest of the Precambrian crust is covered over by younger rocks, and these areas of Precambrian crust that are covered over by younger rocks are referred to as platforms. So we can't walk on them; they're hidden from us. So the vast majority of the central and eastern United States is essentially underlain by Precambrian crust. So underneath all the sediments, all the rocks that are built up on top of it, we have Precambrian crust. So the central and eastern United States is what we refer to as a platform. So there is Archean crust underlying it. So we have shield. That's an area that is of Precambrian crust that's exposed. You can walk on it, you can touch it. And we have platforms. Those are areas of Precambrian crust that are hidden by younger sediments, so we can't touch them. We can't study them unless you drill down. So the shield and platform combined is referred to as the Craton or Craton, depending on how you want to pronounce it. So both Archean and Proterozoic rocks are found in Cratons, and they typically display a felsic to intermediate composition and are dominated by granites and gneisses. So the vast majority of this very early continental crust is granite and gneiss. So Cratons display textures indicating multiple stages of mountain building, metamorphism, and volcanism. So it was, so what we have is, the continental crust that we have is the result of numerous mountain building events. Lots of little pieces of continental crust bang into each other, forming small mountain ranges. Obviously, small mountain ranges lead to regional metamorphism and volcanism. So essentially, the early crust, this Precambrian crust, is very, very strongly deformed and very strongly metamorphosed. However, most Cratons have experienced relatively little deformation since the Precambrian. So once we move out of the Precambrian, we have, obviously, as I said, material that's getting stuck onto the side of this craton that makes up the cores of each continent, and there's material being deposited along the margins of the craton from, by rivers. We have sediments being deposited. That's also adding new material, new mass to the margins of these continents. And this new material that is deposited after the Precambrian essentially acts as a buffer. So, every time there's an impact that occurs after the Precambrian, the new material takes the force of the impact. The Craton itself, that just sits there unaffected. So, after the Precambrian, the Cratons themselves have suffered relatively little deformation. So, as I said, the exposed Craton in North America is termed the Canadian Shield because it's almost completely in Canada. And it covers most of northern and northeastern and central Canada, a large part of Greenland, the Adirondack Mountains in New York State, parts of Minnesota, Wisconsin, Michigan, and there's little bits, as I say, in the northeastern states, places like Vermont. So the platform underlies much of North America. However, outside the shield, as I said, these Precambrian rocks are not accessible because they're covered over by younger sediments, except in areas where there has been very substantial uplift, and very substantial uplift can only really occur during mountain building events. So we do find areas of Precambrian crust exposed in the Rocky Mountains and in the Appalachians, because those are areas where large pieces of rock got pushed up essentially and exposed on the surface. So this diagram here kind of shows you the extent of the Precambrian crust. So you can see the shields are marked out in red, the platforms are marked out in green. So you can see the vast majority of North America essentially is underlain by Precambrian crust. Now all the stuff that's here in brown, in this kind of tan colour, that's material that's been added post-Precambrian. So as you can see, down here in Texas, you can see that we are actually, sitting on new material that has been added later on. But you can see just how important this Precambrian crust is to the formation of the continents. So it's been 40 minutes. This is a good time to take another break. So pause the presentation. Once again, get up, have a walk around, get a glass of water, and come back in a couple of minutes, please. All right, so now let's start thinking about Archean rocks in the Cratons. So Archean rocks account for only about 22% of the exposed Precambrian crust. And the largest exposures of Precambrian crust from the Archean are in North America and Africa. So the Archean rocks are dominated by greenstone belts and granite gneiss complexes. So greenstone belts are dominated by a type of rock called greenstone. It's a metamorphic rock that's formed from the metamorphism of basalt. Whilst granite gneiss complexes are, obviously as the name suggests, dominated by granite and gneisses. Both of them typically have a composition that's dominated, mineral composition that's dominated by quartz and feldspar. And granite gneiss complexes are by far and away the most common type of crust that we have from the Archean. So the granite gneiss complexes are mostly granitic gneisses and granites. So essentially you have gneisses with the composition of a granite. And they were probably derived from felsic to intermediate plutons emplaced in volcanic island arcs and mountain ranges. Now, the greenstone belts, on the other hand, they account for only about 10% of exposed Archean rocks. However, they are considered, they are considerably more important in terms of the information they can give us, because they tell us a lot about the deformational history. But they're also important because they are hosts for significant deposits of gold, silver, copper, lead, and zinc. So first of all, let's think about the formation of the continental crust. So the continental crust, essentially, as we saw in the diagram a couple of slides ago, we could quite clearly see, these cratons are very, very large. So the question is, well, how did we form these very, very large areas of rock? And the answer is, once again, it's accretion. It's lots and lots of small pieces of crust coming together, eventually building up to form a very, very large piece of crust. And so, what were these small pieces of crust? The answer is, these small pieces of crust would have initially been island arcs. So as we were saying, these very, very early pieces of early crust would have occasionally subducted. As they subducted, just like as they do now, they would have melted. That would have essentially produced a felsic to intermediate magma that would have fed felsic to intermediate volcanoes on the surface. And obviously it would have meant that large bodies of granite would also have become emplaced underneath these volcanic arcs. And essentially it would have meant that you end up with a whole, essentially a landmass here that consists of intermediate and felsic igneous rocks. And of course there would have been sediments either side of these island arcs produced by the erosion of the volcanic rocks. And so every once in a while, through the process of plate tectonics, one island arc would have found another island arc, and the two of them would have smashed into each other, and they would have combined together to form a piece of continental crust. Then another island arc comes along, that smashes in, and that adds to the general mass, and over time, lots and lots of little island arcs get added, and the core, this craton, becomes larger and larger and larger. The interesting thing is that every time one of these impacts occurs, essentially you end up forming a small mountain range, and obviously that leads to lots of metamorphism, and so that helps to explain, number one, why these Archean rocks are very heavily metamorphosed, and it also helps to explain why they're very strongly deformed, because all these impacts would have led to very strong deformation of the continental rocks, of these Archean crustal rocks. So this is where the continental crust comes from. It's rather straightforward. It's not a complex idea to understand. So now we need to think about the greenstone belts. I should have said, so this stuff here, this is going to be mostly the granite and the gneiss. So the question then becomes, where's the greenstone coming from? Well, as I said, greenstone belts are formed by the metamorphism of basalt. So a greenstone belt consists of 3 main rock associations. So it's split into 3 distinct layers. The lower and middle portions are mostly volcanic. So they were basalts that have now been metamorphosed to produce greenstone. So the lower and middle portions of a greenstone belt are the greenstone. The upper layer of a greenstone belt is mostly sedimentary. And now those sedimentary rocks have typically been metamorphosed, but nevertheless they were sedimentary or possibly pyroclastic. Maybe they were of a volcanic origin. And then this entire sequence, of 3 distinct layers, is then commonly intruded and cross-cut by granites and big thrust faults. So greenstone belts tend to be synclines, so they tend to form these elongate troughs, and they measure between 40 and 250 kilometers wide, and 120 and 800 kilometers long. So they have a very elongate morphology, which explains why they're referred to as belts. So this diagram here kind of shows you, what we're talking about. So to start with, they form these synclines, so they have these troughs, and they are split into 3 distinct layers. So we have this lower layer here. That's going to be typically mostly basalt with maybe some peridotite. Now, to be clear, once again, they have been metamorphosed, and so those layers of rock are going to be green schist. Then we have the middle layer here, marked out in this brown colour. That's going to be middle volcanics, mainly basalt, once again, metamorphosed to give us greenstones or green schists. And then in this kind of yellow colour here, we have the upper unit. That's going to be sedimentary rocks, or maybe pyroclastic rocks, so volcanic rocks, that once again have been metamorphosed. So this area here, we're going to get essentially metamorphosed sedimentary rocks, things like quartzites, maybe some gneisses in there as well. And you'll see these 3 sequences have been folded to give us this syncline. Then everything gets intruded by later granites that cut through the sequences. And synclines are separated by areas of granite and gneiss. So each of these synclines will be separated from one another by a body of granite and gneiss that runs through the middle and splits them up. So if we look at this map here, this is a map of Canada, and you can see the greenstone belts are marked out here in dark green, and you can see between the greenstone belts there's one, there's another, there's another, there's another. They're separated by these areas of lighter green. Those are going to be the granite gneiss complexes. So the greenstone belts essentially occur in isolation from one another. And so there's a general trend, you can kind of just about see it there. So there's the approximate trend of the Canadian greenstone belts. It's running approximately northeast-southwest. So the volcanic rocks of the lower and middle portion, as I said, would have been mafic to ultramafic in composition, but of course they've been metamorphosed. And that they've been metamorphosed to low to medium grades. And this gives rocks a distinct green colour due to the crystallization of three green minerals: chlorite, actinolite and epidote, and these three minerals essentially are used to define green schist facies. So the rocks that are formed from by the metamorphism of the basalt gives us a green schist, or greenstone. They're essentially the same rock. Green schist has a foliation, greenstone does not. So the greenstones form from a basaltic protolith, and they display a pillowed texture indicating subaqueous formation, which essentially means they're seafloor basalts. So the basalts that are making up these lower and middle portions of the greenstone belts were erupted onto the seafloor. So these are modern pillowed basalts here, and these are pillowed basalts in a greenstone belt. And now it's a bit difficult to see, but what you can see is you can see the kind of lumpy shape that some areas have. You can see the kind of lumps there, the kind of rough circles. You kind of see an edge of one coming around here as well. And these are the pillows. Now in this case they've been cut through. So you're looking at a pillow that's been sliced through when you look at something like this. We're looking at it, as if they're taking a slice across here. And also over in the sequence we will find metamorphosed komatiites as well. So if you remember, komatiites are these ultramafic volcanic rocks. So this tells us that we not only had mafic volcanism, we also had ultramafic volcanism as well. So the presence of ultramafic rocks within the lower and middle sequences essentially shows us we had to have had komatiites. And komatiites are very, very high temperature magmas. They would have had a temperature of around 1,600 Celsius maximum. So in contrast, just compare that to the maximum possible temperature of a basaltic lava flow that sits somewhere around 1,400 Celsius. Most basaltic flows will have a temperature in the region of about 1,200, 1,300 Celsius. So the fact that we have these komatiites being erupted tells us something quite interesting. It tells us about the temperature of the Earth's mantle at that time. So the Earth's mantle at that time was exceptionally hot, and that meant that the Earth's mantle could melt in quite large volumes, because obviously the Earth's interior was hotter because we had more heat from the heat of accretion and more radioactive isotopes. So it meant that mantle temperatures were about 300 Celsius higher than the present day. So at these very, very high temperatures, the mantle could melt more easily, it could produce magmas in greater volume, and because more of the mantle could melt, it meant that the magmas produced were not mafic, they were ultramafic. They were very, very iron and magnesium rich. And so this meant that these very, very large volume ultramafic magmas could move through the crust and be erupted onto the Earth's surface, forming komatiites. Now, as the Earth's interior has cooled, the Earth's mantle is no longer capable of forming ultramafic magmas in very, very large quantities. So this means that when we do form ultramafic magmas now, well, yes, they will start to rise up. They might make it into the crust, but unfortunately they don't have enough volume to make it all the way to the surface before the magma cools down and solidifies. So that means, unfortunately, no more komatiites anymore. The Earth's interior is just too cold. So the upper portion of the greenstone sequence of the greenstone belt is made up of metamorphosed sedimentary rocks, or possibly metamorphosed pyroclastic rocks. So the sedimentary rocks that we can see are dominated by essentially greywackies, so muddy sandstones and mudstones. And within these rocks, where we have portions of them that are less metamorphosed, so we can start to see the original structures, we can see very, very small scale cross bedding. which indicates that whatever was depositing these sediments was just moving in one direction. So we think, bearing in mind the fact the sediments are made from, or at least were, greywackies, and they contain a unidirectional flow, it suggests that quite a lot of the material that makes up these upper sedimentary rocks would have been from turbidite sequences. So if you remember what those are, they're the underwater landslides that come off the continental slope down onto the continental rise. Now, of course, this makes a lot of sense, because if the middle and lower portion of the Greenstone belt represents oceanic crust, well, that pretty much means that the majority of any rock that's deposited on top of it would be either deep marine rocks like mudstones, or the kinds of rocks that we get essentially at the continental rise, which would mostly be greywackies deposited by turbidites. So it all falls into place. The vast majority of material that makes up greenstone belts is from a marine environment. Now, within these sequences, we do sometimes get sandstones, limestones, and banded iron formations. Now, that would suggest that in some cases, the upper portions of this greenstone sequence are actually forming in shallower water depths. So, not every single greenstone belt formed in a deep marine environment. Some of them will have formed in a marine environment with slightly shallower water. So, so this holds fast. This is true in the vast majority of cases, but occasionally some of them will have formed in slightly shallower water. So the next question becomes, well, how did greenstone belts actually form? Well, greenstone belts occur as terrains which consist of multiple parallel belts, each separated from the next by a granite gneiss complex. So if you remember a couple of slides ago, we saw that map of greenstone belts in Canada. Essentially, all the greenstone belts are orientated approximately parallel to each other, and they're all separated by these granite gneiss complexes. So when we try and explain the formation of greenstone belts, we have to be able to explain that alignment. So we also have the volcanic rocks, which are now metamorphosed, that make up the greenstone belts, were deposited in a number of different tectonic settings. So sometimes we see basalts that seem to have been deposited at mid-ocean ridges. Some basalts appear to be associated with island arcs. Some volcanic rocks appear to be associated with back arc basins, which we'll cover in just a second. Some of the volcanic rocks appear to be oceanic plateaus. That's areas where you have flood basalts pouring out onto the seafloor in huge quantities. And some of the basaltic material appears to be related to rifting of continental crust. So the basaltic material did not just form in one type of environment. There is lots of different types of environments in which basalts were being deposited to form the lower and middle portions of greenstone belts. So we are actually going to deal with the two preferred models for greenstone belt formation. Now, these two preferred models are not going to be able to explain how you get all these different types of basalts in some greenstone belts. Okay, they're a best fit for the evidence that we have. Okay, so there are two dominant models. The first one is the back arc model. Now, in this model, a back arc forms and fills with basalts and sediments. So you're thinking, well, hold on, what's a back arc? Okay, so let's jump to the next slide first. Okay, so here we go. So this is the situation. So here's our subduction zone. The oceanic crust is coming along, subducting under here, melting, producing a line of volcanoes at the surface, producing an island arc. Okay, so we have an ocean subduction zone producing an island arc. We're all familiar with that from earlier on in the course. Now, what can happen is the piece of subducting oceanic crust can begin to roll back. Okay, so the angle of subduction can begin to become steeper. So as this crust begins to roll back and the angle of subduction becomes steeper, it means that you begin to open up a void between this piece of oceanic crust and the subducting piece of oceanic crust. Now that void has to be filled. And so in order to fill that void, what happens? Well, the volcanic arc has to stretch itself, has to extend itself to fill the void that's created. Now, as it stretches itself to fill this void, that means that the island arc begins to go into extension. It begins to become stretched. And so if the slab rollback continues, the island arc will become more and more stretched, and eventually you will build up a basin in between the two halves of the island arc. And if you stretch the crust thin enough in this basin, the mantle underneath will begin to melt through decompressional melting, and the magma produced will rise up into the basin and be erupted onto the seafloor in the form of basalts. So here's a modern example now. So this is the Lao Basin. So you can see here's the island of Tonga over here, island of Fiji over here, and here's the northern end of New Zealand down here. And you can see, so here's a subduction zone there. You can see the trench running along here. And you can see that if you look at the picture, you can see you've got one line of essentially volcanic rocks here. And you have another line of volcanic rocks here. And in between them, you have this relatively flat area of seafloor. Now, if we zoom in on that flat area of seafloor, so once again, here's Tonga over here, there's Tonga there, and we have the Fijian Islands essentially going to be just over up off here towards the top left. What you can see is the seafloor in between has got all of these parallel cracks in it. That's a strong indicator that this area of crust is being actively extended, it's being stretched, and it's fracturing, and you get lots of parallel lines all running next to each other. Okay, these are all the cracks, all the faults produced by extension. And once the crust becomes thin enough, the magma underneath will melt, basalt will begin to rise up, and it will begin to flood out and onto the floor of this back arc basin. And so this is what we mean when we're talking about a back arc basin. So when your island arc begins to extend, essentially it will split into two, and you get this area of extension in between. So you get one half of the island arc at the front and one half of the island arc at behind. You have this basin in between. That's the area of extension. This crust here is getting stretched. Eventually the mantle underneath will begin to melt through decompressional melting, which allows basalt to float, which allows mafic magma to flow to the surface, where it will be erupted into the basin, the back arc basin, in the form of basalts. So that explains where the lower and middle portion of the sequence comes from. So then we just have to explain where the upper portion of the Greenstone sequence comes from. Well, that's going to be mostly felsic clastic rocks, lots of quartz, lots of feldspar. Well, that's relatively easily explained because the island arc itself is going to be made of felsic and intermediate igneous rocks. When you erode those, you are going to produce large quantities of clastic sediment, and that clastic sediment is going to go into the back arc basin, and that's going to produce the upper layer of the Greenstone belt. So essentially we have our three layers: lower basalt, middle basalt, and sedimentary rocks on top. And so then what happens? Well, eventually what will happen is that the back arc basin will close. It will be squished again. Okay, so it's been opening. So initially it undergoes extension and becomes bigger. Eventually it will then undergo compression, and the back arc basin will be squished. And as it gets squished, it will obviously cause the back arc basin to fold, producing the syncline. So the back arc basin model is actually pretty good. It explains the three layers. It explains where the sedimentary rocks come from, and it explains how we form the synclines. And then later on, it also helps to explain, later on, once this has all happened, this syncline then gets intruded by large quantities of granite. And it also helps to explain the granite gneiss complexes, because once again, if we go back to this picture here, essentially each one of these rows of islands essentially is made up of granites. It's felsic and intermediate volcanic rocks. And so these back arc basins won't just form once, they will form again and again and again at the same location. And so this could explain how you can get multiple synclines all running parallel to each other in the same area, because you get them being formed again and again and again, essentially parallel to the same subduction zone. So it's a relatively neat model, and it helps to explain pretty much everything that we see. So that's the dominant model and the one that most people favour when talking about Greenstone belt formation. The other model is the island arc model. So the island arc model simply says that the Greenstone belts are the result of a pile-up of volcanic arcs. Okay, so this model here kind of pretty much shows you what the basic idea is. So we have an island arc here. It's stuck onto the side of a piece of continental crust. And we have a subduction zone that's coming down underneath it. We have another island arc that's on the piece of that's on the piece of subducting crust, and eventually subduction will pull this island arc this way, and it will eventually hit this island arc here, and the two will stick together. That's the basic model. Now, in between these two island arcs, you have an area of seafloor that's covered in sedimentary rocks. Okay, so lots of clastic sediments in this area. So these clastic sediments will get squished between the two island arcs as they bang into each other, and that's going to produce our granite gneiss complex. Now, you're instantly thinking, hold on, that doesn't make much sense. because we just discussed how the Greenstone belts are made up mostly of mafic igneous rocks, but the island arcs are going to be mostly felsic and intermediate. So that's a bit of a problem for us. So how do we explain that? Well, the thing is yes, although the island arcs themselves are felsic to intermediate in composition, they are going to be sitting on the oceanic crust. So the fact they're sitting on the oceanic crust, that helps to explain where the lower and middle portions of the sequence are coming from. Then the upper portion of the sequence, which consists of clastic sedimentary rocks or maybe pyroclastics, that comes from the island arcs. And so that helps to explain how we get our 3 distinct layers as part of our greenstone belt, even though, common sense would suggest that the island arc itself should be dominated by felsic and intermediate volcanic rocks, and therefore we shouldn't have greenstones. Now, obviously, because we have continued subduction, it means lots and lots of granites will be produced, and those granites will then intrude the greenstone belt, and that makes perfect sense. Obviously, also the impact between these 2 island arcs will cause lots of tectonic deformation and the formation of lots and lots of synclines. And so now this model, on the other hand, this model is the preferred model to explain the Canadian greenstone belts. Okay, helps explain the nice, repeating pattern. So greenstone belt, granite gneiss complex, greenstone belt, granite gneiss complex, etc. And so this model, explains, as I say, the Canadian options. However, it doesn't really apply to that many other areas. So on the whole, the back arc basin model is probably the better one, but in terms of the Canadian greenstone belts, the island arc model may well be the superior choice. Okay, so it's been over an hour, so once again, time to take a break, pause the presentation, get up, have a walk around, go and get a glass of water, and come back in a few minutes, please. Okay, so now let's think about Archean plate tectonics and the continued development of Cratons. So during the Archean, like the Hadean, the Earth's lithosphere was probably thinner, hotter, and more buoyant. And this means subduction would have been quite difficult, if not impossible. So just think about it this way. If the Earth's mantle is very, very hot, it naturally wants to rise. So if you're trying to subduct something down into it, if you're trying to push down a piece of crust into that mantle, it's going to be a lot more difficult than it is now, because the very hot mantle during that time is going to be pushing up. So it makes subduction very, very difficult. So the types of tectonics during the Archean would probably have been a little different to modern processes. So the other thing that we have to take into account is the Earth's interior was hotter during the Archean, and that would obviously lead to faster mantle convection and faster tectonic processes. So during the Archean, the continents, which we now refer to as the Cratons, grew rapidly, and 2 processes will have helped with the rapid growth of these Cratons. The first one is the one we've already discussed, continental accretion. Just island arc after island arc sticking onto the side of these Cratons, making them larger and larger. Now this is going to make the Cratons more laterally extensive. It's going to make them broader, okay? It's not going to make them any thicker though, really. So if you want to increase the thickness of these Cratons, we do that through underplating. So underplating essentially increases the volume of the Cratons. Essentially, it's produced by magma, which is the result of subduction. So obviously, we have subducting piece of oceanic crust going underneath these very early continents. Now, as I said, subduction would have been difficult, not impossible, but difficult. So we would have had some subduction going on. Obviously, the piece of oceanic crust would have been subducting down into the mantle. It would have melted, or it would have caused the mantle to melt, shall I say, and that would have then produced magma that would have risen up, and it would have become stuck at the base of the continental crust. It would obviously start to melt the continental crust, producing felsic and intermediate magmas. So essentially, we have bodies of mafic magma that get stuck underneath the continental crust, and we have these felsic and intermediate magmas, plutons that are rising through the continental crust, and essentially all of these, bodies of magma, quite a lot of them get stuck and never make it to the surface. And so that big ball of mafic magma stuck at the base of the crust slowly cools and solidifies and sticks itself onto the bottom of the continental crust. And obviously all these big granite and diorite intrusions within the crust also cool and solidify, helping to add mass to the continental crust, to this very early craton. So these two methods here help to make the craton more laterally extensive and also thicker. So when did proper stable plate tectonics begin to occur? Well, that's a tricky one to answer. So the first indicator of plate tectonics is the presence of ophiolites. So if you remember, an ophiolite is when oceanic crust is not subducted, it is abducted, so it's pushed onto the continental crust. Now, when you think about it, that kind of makes sense, because as I was saying, it would have been quite difficult to subduct rock into the mantle during this time period. So obviously, if you can't subduct it, but you have two pieces of crust pushing into each other, well, the only thing that can happen is one piece of crust has to go over the other. So typically, in the modern case, the piece of continental crust would go over the piece of oceanic crust, and you'd have subduction. If you can't do that, the only other option is to have the oceanic crust go over the top of the continental crust, and that's the process of abduction. So abduction forms ophiolites. So when we look at ophiolites, we begin to see their appearance. The ophiolites become less common after about 1 billion years, and the earliest example is the Ishura Greenstone belt, which is about 3.8 billion years old. So we know we definitely have to have plate tectonics by 3.8 billion years, because we have ophiolites forming. So we know at this point we definitely have to have pieces of crust moving about, and we know from the fact that we have ophiolites, those pieces of crust must have been banging into each other. So the evidence we have agrees that some kind of plate tectonics was definitely around by 3.8 billion years. It was definitely occurring probably by about 3 billion years, and before this 3.8 billion year mark is a little bit uncertain. Plate tectonics probably would have been rather chaotic at that point. So, so we can say with relative certainty, yes, some plate tectonics by 3.8 billion years, probably becoming established and more normal by about 3 billion years. And by 1 billion years ago, plate tectonics would pretty much have been running as it runs now. So, as I was just saying, by about 2.7 billion years ago, we have proper plate tectonics underway. So by this point, we have strong indicators of subduction. So we know that things are subducting down into the mantle, maybe not easily, but it is happening nonetheless. So there were differences compared to the modern systems, though, the most obvious of which was that during the Archean, sediments weren't being deposited along passive continental margins. So what do I mean when I say that? Well, typically the edges of the continents fall into one of two possible groups. The first one is a passive continental margin. Now that's like the eastern seaboard. Okay, there's no mountain building there, there's no subduction. Essentially, sediment is deposited onto the coast into a nice, calm, stable environment. So that's a passive margin. Now compare that to the western margin of South America. So in the western margin of South America, you have a very big subduction zone. There's a Nazca plate subducts underneath the South American plate. Now that margin is active. There's mountain building, volcanoes, earthquakes. It means that because it's so active, lots of stuff is going on, and it means you can't have a nice kind of, safe environment in which you form nicely layered sedimentary rocks. So the sedimentary sequences you get in that kind of environment are often very, very badly deformed, very strongly folded, very broken up and disjointed. Compare that to a nice passive margin like the eastern coast of the United States. You'll get nice horizontally bedded sediments, nice well-defined sequences that are laterally extensive. So there are these two distinct sets of environment. Now, when we look at the continental margins of the continents from the Archean, what we see is a distinct lack of passive continental margins. They're just not there. So this means that we see very few marine sandstones, marine mudstones, and marine carbonates. So what this would suggest is it would suggest that the continental margins of the Archean continents were all active. So each continent would have been nearly completely ringed by a subduction zone. And so this would also have helped to increase the rate of continental accretion, because if oceanic crust is subducting under each continent, well, that's naturally going to pull island arcs towards those continents. And it also means that, of course, if there's a subduction zone going underneath the continents, well, that, of course, means there's going to be melting underneath the continents, which is going to supply magma, which is going to help with the underplating of the continents, helping to add mass to them. So we don't see passive continental margins really making an appearance until the Proterozoic, where they become a lot more common very quickly. So we have no idea how many continents were actually present during the Archean. So through accretion and underplating, these continents had probably about 30 to 40% of the volume of the modern continental crust by about 2.6 billion years. That's the end of the Archean. And these continents formed larger land masses, otherwise known as supercontinents, during the Proterozoic. So, although it's not 100% certain, it seems likely that there were two large land masses, so supercontinents, that were present in the mid to late Archean. And they've been named Valbara, which existed between 3.1 and 2.8 billion years ago, and Corneland, that existed about 2.7 billion years ago. Now, to be clear, the evidence for these two supercontinents is a bit sketchy, to say the least. Okay, we do think there is a chance they were there. You know, common sense says yes, they probably did form, but the evidence is not strong. So, you know, don't take it as gospel. So we see the formation of these proposed land masses by looking at the orientation of metamorphic textures and the timing of metamorphism and crustal melting resulting from their formation. Because obviously when two pieces of crust bang into each other, you typically produce a mountain range. And a mountain range will have obviously large quantities of regional metamorphism. Obviously, the two pieces of crust will show indications of having banged into each other, so we'll have metamorphic textures which have the same orientation, and those and the rocks will also have undergone the same sequence of melting at the same time. So we can link those two pieces of crust together and say yes, once upon a time they were in direct contact with one another. So what we see is between 3.2 and 2.6 billion years ago, we see deformation and metamorphism in the snowbird tectonic zone, which is in the northwest portion of the Canadian Shield. Okay, so that's an indicator that in that zone we had two pieces of crust coming together. And the area displays granulite facies metamorphism. So that's high temperature, moderate to high pressure metamorphism, so most commonly associated with mountain building. And that suggests that there was some kind of very large orogenic event. And large orogenic events are pretty much the result of two big pieces of crust banging into each other. And so that would suggest if you've got more than one, if you have two pieces of crust or more bang into each other, then you have a supercontinent forming. So we also see Archean rocks from Wyoming, Montana, and the Mississippi River Valley displaying deformation consistent with continental accretion. So we know with certainty that there were bits of crust banging into each other, forming continents. Now the question is, were they really big enough to form what we refer to as a supercontinent? That's debatable, but there were definitely bits of continental crust banging into each other and suturing, sticking themselves onto each other. Okay, so what about the Archean atmosphere? Well, the Earth's very earliest atmosphere was composed of hydrogen and helium, and that's a reflection of the gas cloud that collapsed to form the Sun. So when I say the Earth's earliest atmosphere, I'm talking about the Earth's earliest atmosphere here. So this atmosphere would have been extremely tenuous and it would not have lasted long at all, for two reasons. First of all, the Earth's gravity is insufficient to retain hydrogen and helium. They're just too light. For the Earth to be able to retain hydrogen or helium, it would need to be about 16 times larger, so should I say 16 times heavier than it is at present. So, we don't have the gravity. The other thing is that during the very early portion of Earth's history, we didn't have a core. If we don't have a core, we don't have a magnetic field, so we don't have a magnetosphere. And magnetosphere obviously protects us from the solar wind, this stream of particles that comes constantly off the sun. So, of course, without the magnetosphere to protect our atmosphere would constantly have been pummeled by this solar wind, and that would have slowly stripped away the atmosphere as well. So the Earth's earliest atmosphere would have been hydrogen and helium, but it would have been lost very, very quickly. Just to show you, how this works. So here we have a diagram, temperature here, escape velocity here. So that's essentially the escape velocity for the gases. And as you can see, we have these coloured bands cutting across the diagram. So we have xenon, carbon dioxide, oxygen, nitrogen, water vapour, ammonia, methane, helium and hydrogen. And overlaid in this diagram, you can see individual planets and satellites. And you can see that as the mass size of the planets go up, their ability to retain certain gases increases. So a small body like the moon has sufficient gravity to retain xenon. It has insufficient gravity to retain carbon dioxide, oxygen, nitrogen, water vapour, etc. In contrast, the Earth has sufficient gravity to retain xenon, carbon dioxide, oxygen, nitrogen, water vapour, ammonia and methane, but insufficient gravity to retain helium and hydrogen. Now, the four gas giants, on the other hand, have sufficient gravity to retain all of these gases. So once we did actually get a core, and therefore we had a magnetosphere, we had essentially a barrier that protected us from the solar wind, and this meant the Earth's atmosphere could begin to form. So the Earth's atmosphere formed through the process of outgassing. So that's the process of releasing gases from the Earth's interior via volcanism. And so when volcanoes were erupting, they would release large quantities of water vapour, nitrogen, hydrogen, and carbon dioxide into the atmosphere. So this would be essentially what the Earth's early atmosphere was dominated by. So the volcanic gases, as I say, were dominated by water vapour, carbon dioxide, hydrogen sulfide, sulfur dioxide, carbon monoxide, sulfur, hydrogen, chlorine, nitrogen. So a real mix of different gases. So carbon dioxide and carbon monoxide and nitrogen would have reacted with the hydrogen, and that would have produced methane and ammonia. The one thing you'll notice is definitely missing from this sequence of gases is, of course, oxygen. So we are pretty certain that oxygen concentrations in the early atmosphere, the Archean atmosphere, would have been extremely low. And we know this because of the presence of two minerals in the detrital sedimentary rocks from this period. So where we find clastic sedimentary rocks from the Archean, we see that they contain the minerals pyrite and uraninite. So the thing about pyrite and uraninite is they are both unstable in oxidizing environments like the atmosphere we have now. So our current atmosphere is about 21% oxygen. So that means there's lots and lots of oxygen. So minerals like pyrite and uraninite will very quickly react with that oxygen and they will break down. The fact that they are in these clastic sedimentary rocks from the Archean means that there cannot have been large quantities of oxygen around. If there had been, they would not have been able to survive, but they could because there was very little oxygen. So that's a very strong indicator that the Archean atmosphere was very, very, very oxygen poor. So we see pyrite and uraninite disappearing as we move into the Proterozoic, and that's an indicator that during the Proterozoic the amount of oxygen in the atmosphere goes up. And that's also backed up by the fact that during the Proterozoic we start seeing the formation of large quantities of iron oxide minerals, like hematite and goethite. And that's another strong suggestion that during the Proterozoic, oxygen concentrations go up considerably. But anyway, we're focused on the Archean right now, and during the Archean, the amount of oxygen in the atmosphere is pretty tiny to near non-existent. So the oxygen that was in the atmosphere during this period came from two sources. The first one is photochemical dissociation, and that's when ultraviolet radiation from the sun hits a water vapor molecule in the atmosphere, and it splits that water vapor molecule into oxygen and hydrogen, and when two of these oxygen atoms combine, it will form an oxygen molecule as we have in the atmosphere now, and we breathe. And that accounts for approximately 2% of present-day oxygen formation. So it creates a relatively small amount of oxygen. Now, the interesting thing is that rates would have been a lot higher in the Archean because there was no ozone layer. The ozone layer absorbs ultraviolet radiation, so it wasn't there in the Archean. And so this means the Earth's atmosphere would have been hit by more ultraviolet radiation. That means more water molecules would have been split, and that means more oxygen would have been produced through photochemical dissociation. Important point to note though, it still would have been an absolutely minute amount of oxygen. Okay, very, very little. The other method for producing oxygen is, of course, photosynthesis. During the Archean, we do have indicators that there were photosynthesizing organisms around. And those organisms obviously would have taken carbon dioxide, water, nitrogen, phosphorus compounds, and used them to produce sugars. And oxygen was produced as a waste product. But once again, the amount of oxygen being produced through photosynthesis at this point would have been relatively limited. So we know that photosynthesizing cyanobacteria, that's blue-green algae, were present around, give or take a bit, 3.5 billion years ago, because we have a type of fossil which we refer to as a stromatolite. However, concentrations of atmospheric oxygen did not become significant until about 2.6 to 2.7 billion years ago. That's during the Proterozoic, and at that point we start seeing the formation of iron oxide-rich rocks called banded iron formations, and we start seeing changes in the in isotopic carbon in sediments. So this diagram here kind of sums up photochemical dissociation. We've already discussed it, so we're not really going to worry about it too much. We're going to skip through that. Okay, so we were just discussing photosynthesis, and obviously photosynthesis requires life. So the next question is well, during the Archean, that's when life first made its appearance. And I'm going to be honest, the next part of the presentation is not particularly straightforward, and it's particularly unsatisfying because there are lots and lots of questions that are still unanswered. Okay, so when did life first appear is the first question. Well, we have a definite monomer, that's a single-celled organism with no nuclear membrane, and we have definitive fossils from 3 billion years ago, and we have probable fossils going back to 3.5 billion years ago. And there are some geochemical indicators that suggest that life could go all the way back to 3.8 billion years ago. So there's a layer of graphite in the Ishura Greenstone belt which suggests that it could have been made from organic carbon, and that dates to 3.8 billion years ago. So we know for certain we had life 3 billion years ago. It's probable we had life 3.5 billion years ago, and maybe we had life 3.8 billion years ago. So we've covered evolution, so we have some idea what happens once we have life. But we need to think about how life actually originated. Okay, so the first stage is the process of abiogenesis. So this is the process of forming a living organism from non-living matter. So weirdly, abiogenesis is not actually a random process, as natural selection functions at some level. So some abiogenic reactions will be successful, some abiogenic reactions will be unsuccessful. So essentially there is a natural selection to that process. So abiogenesis does not mean that we instantly have a fully formed cell or even complex molecules straight away. So instead what we have is a process that requires billions of steps, each one increasing the organization and complexity of the thing that's being built in very, very small increments. So you have to remember, in the case of the Earth, we would have, the Earth essentially is a giant machine for doing this. And we would have had, billions, trillions of reactions happening every minute, most of them failing, some of them being successful, taking us to the next stage. Most of them will have failed, then a few of them will have been successful, then most of them will have failed, then a few of them might have been successful, and so on. And you can see it takes millions and billions of little steps to make it to the point where you actually have a complex organism like a bacteria. So as I said, this was occurring over the entire planet with billions of reactions happening every second. So eventually you're going to hit on the right solution through, blind luck and a certain amount of, selection. So essentially, you have lots of attempts that fail and only a few attempts that are successful. So when is something actually considered to be alive? Well, there are 7 criteria that something has to meet in order to be considered alive. The first one is it has to be able to maintain balanced conditions in its inner structure. It has to be able to achieve what we refer to as homeostasis. So, in the case of human beings, if we get too hot, we get in very serious trouble. You get too hot, you get heat stroke. If you get really hot, it can kill you. Essentially, if your internal conditions become imbalanced, it can be very, very detrimental to you. Number 2, an organism should have a highly organized structure. Number 3, it should be able to break down or build up nutrients, so it has to have metabolism of some kind. Number 4, it should grow, so its structure should change over time in an advantageous manner. Typically, the organism in question will get larger. It should show adaptation to its host environment, so these adaptations will occur over time. It should respond to environmental stimuli on demand, and it should be able to reproduce. And so we've got 7 criteria that need to be met, but when it really comes down to it, number 3 and number 7 are the ones that we're going to aim for first. It should be able to break down and build up nutrients, and it should be able to reproduce. That's what we need to be able to, that's what we need to be able to achieve first, and then the other 5 will kind of fall into place after that. So the origin of life. So if life is to originate, you need to synthesize organic molecules from the available chemical elements. So the elements available were water, carbon dioxide, nitrogen, ammonia, methane, hydrogen sulfide, sulfur dioxide, and phosphorus. So there's plenty of material about. And so that means we have sources of hydrogen, carbon, oxygen, nitrogen, sulfur, and phosphorus, and that's pretty much what we need to build our cells. So the starting materials are all there and they are in abundance. So great, we've already met that requirement. So the organic molecules formed from these simple building blocks are called monomers. And a classic example of a monomer is an amino acid. That's probably a term you've heard. And these amino acids are the building blocks of more complex, larger organic molecules. So in the 1950s, a scientist called Stanley Miller took a gas mixture approximate to the composition of the Earth's early atmosphere and subjected it to electric sparks to simulate lightning. So his equipment was rather straightforward. So he had a system where he was boiling water here that would push water vapor up here, so he had a constant circulation of gases going on. In this chamber here, he had 2 electrodes. He would pass an electric current between them to simulate lightning. And within the chamber here, he had a mixture of water vapor, methane, ammonia, water, and hydrogen. And the resulting particles, the resulting molecules that formed would obviously be swept down here, and they would become trapped down here in what's referred to as the trap. So Stanley Miller ran this experiment, and after a few days, he realized that the trap down here at the bottom was becoming cloudy. So initially he thought that he hadn't cleaned the glasswork well enough, so he took his experiment to pieces, cleaned it all super well, and then he started the experiment again, and exactly the same thing happened. He ran it several dozen more times, and the same thing happened every time. The water down here in the trap became cloudy. And so obviously he then took that water, he tested it, and he found that water contained several essential amino acids. So it had several of these building blocks that are required for organic organisms, for cells to form. So we've done the same experiment recently using the same setup and a slightly different gas mix. And using the slightly different gas mix, we've managed to produce nearly all of the 20 amino acids required by living organisms. So we can pretty much make every amino acid we need just by lightning in the atmosphere. So that's a great thing. So that gets us around problem number 1. How do we make these monomers? The answer is, well, lightning. So amino acids may also have been synthesized by ultraviolet light strikes, or possibly by addition from comets. So we have some good evidence to suggest that the ice that makes up a comet is not only water ice and carbon dioxide ice, etc. There will also be large quantities of amino acids mixed in with all of that material as well. So that will have also helped to add amino acids into, onto the surface of the Earth during this very early period. So okay, so we can make monomers quite easily. The question is how do we take those monomers and turn them into larger molecules? Well, that's through the process of polymerization. So that's the process by which we take the monomers and we link them together to form polymers. The classic example of a polymer is something like DNA or RNA. So we can make small molecules that are about 200 amino acids long called thermal proteins. And we've been able to do this very, very easily in the lab. So thermal proteins form when an amino acid bearing liquid is heated and concentrated. So essentially what happens is these chains of amino acids become larger as the fluid approaches complete evaporation. So if you think of a situation where you have a small puddle of water which is exposed to the sun, or maybe a puddle of water near some kind of hot volcanic vent, and that puddle of water contains amino acids, well, as that puddle of water begins to dry up, the amino acids will naturally start to polymerize to form these thermal proteins. So once again, this step from taking monomers and forming these polymers, these thermal proteins, is actually a relatively easy step. It's not too complicated to see how that could happen naturally. So when this happens, say the amino acids spontaneously polymerize to form thermal proteins, and the process is modeled to occur at around 70 Celsius, meaning it's likely to have occurred near volcanic systems, which were very common during the Archean. Remember what we said, the Archean crust was probably very, very warm compared to the modern day, and so that helps to explain how we could easily achieve these 70 Celsius conditions. So once again, we can make thermal proteins relatively easily. So things are going quite well so far. So these proteins, of course, were not synthesized by organic processes, so they're considered artificial. So they're actually termed proteinoids. So the problem is that proteinoids will quickly dilute if more water is added. So what we really need to do is we really need to come up with some kind of protective environment in which we can form large quantities of proteinoids and protect them. So to put it another way, what we need is some kind of self-contained chemical system like a cell. It just so happens that if we take proteinoids and we stir up the liquid that they're in, they will naturally clump together. And when they clump together, they form these structures here, which are called microspheres. So microspheres will contain a small quantity of water inside them, and within this small quantity of water, proteinoids can form, and these proteinoids will be protected from the environment around them by the membrane. So essentially we have a nice self-contained system here where more and more proteinoids can be made, and they're protected from the surrounding environment. So microspheres can divide like cells. They can split up. So this microsphere could divide in two to form two cells, or they can combine together. Two cells can come together and they can link up to form one larger cell. So that's not really reproduction in the case, in the biologic case that we would think of it. So are they reproducing? The answer is no. But nevertheless, they are capable of dividing and combining. So microspheres are not usually long-lived structures. Okay, they'll normally last for hours, days, and that's probably about it. But the most important thing is that within the microsphere during that period, you have essentially a factory for making proteinoids in huge numbers. And so when the microsphere eventually pops, the proteinoids go out into the surrounding liquid, and then they, as long as the liquid is agitated, will also then go and form more microspheres, which will then make more proteinoids, which when they pop, those proteinoids will then make more microspheres, and so on. So you can see over time how you can make more and more proteinoids in a fluid, even if that fluid should normally dilute the proteinoids very, very quickly. Now, the problem is these, as I said, these cell walls aren't particularly, these membranes, aren't particularly robust. So if we want a robust membrane of some kind, what we really need is phospholipids. So the next question is when did phospholipids appear? Now, that's a difficult question to answer. However, experiments have shown that when we form proteinoids, we will also form small quantities of phospholipids. And these phospholipids will naturally clump together on clay minerals. So the question is what's a phospholipid? Well, a phospholipid is a molecule that has a phosphorus group at one end and three fatty acids at the other end. You can kind of see it here. The phosphorus group is denoted by the white circle, and it has these kind of these three tails coming off the bottom of it. Those are the lipids, the fats. And so what happens is the phospholipid naturally has a hydrophilic, water-loving, and hydrophobic, water-hating end to the molecule. So the phosphate end loves to be in contact with water. The end that contains the fatty acids does not want to be in contact with water. So if there's water around, the phospholipids will naturally orientate themselves, so the phosphorus groups will be in contact with the water, and the fatty acids will be away from the water. And so that means typically they will naturally arrange themselves into what's referred to as this thing down here, which is the bilayer sheet. Phosphorus groups on the outside, fatty acids protected from water on the inside. And these bilayer sheets will naturally form spheres, which are referred to as liposomes. And this here is a very strong, very robust cell wall. And within here, you're going to have a nice, safe, protected environment in which reactions can take place. Now, the one problem is this. Yes, we can make phospholipids through non-biogenic processes. However, the rate of production is not rapid. So it's a bit of a problem. Now, the thing is once we have cells like this, and once these cells develop the capacity to make their own phospholipids, then we're away. Then things are looking good. However, up until that point, it becomes a bit difficult to explain how you make enough phospholipids to form enough cells. So that's a problem. Got to admit that. Now, as I said, so once we have enough phospholipids though, and we can start forming enough cells that have these bilayers, we have a nice, safe, protected environment in which chemical reactions can take place. Now, the great thing about a phospholipid bilayer sheet is that it has holes in it. And these holes will let small molecules in, but they are not big enough to let large molecules out. So we can bring in material, we can bring in small molecules into the cell, and we can use those small molecules to make larger molecules, but those larger molecules cannot escape. And so it means the interior of these cells made from this phospholipid cell wall essentially will build up a soup of proteins in the middle of them. Now, at this point, we are moving very, very close to having what we would consider to be a very simple cell. So we have the membrane, so we have the protected layer, and we have the interior, which essentially, within this interior, we have lots of reactions taking place, producing lots and lots of proteins and other molecules. So, okay. So we have lots of monomers, and these monomers are polymerizing inside a protective environment most dominantly like a liposome. So the next question is how did reproduction start? So microspheres do divide, but they only break into smaller units. So that's not true organic division. That's just a microsphere splitting up. So an important point to note is we do not require DNA or RNA to reproduce. Okay, so the process of reproduction can actually predate DNA and RNA. However, once DNA and RNA do make their first appearance, we have to be able to split them in order to divide them, to split them between the two new cells that are forming. The problem is you can't do that without enzymes. The problem is you can only really make large, complicated enzymes if you have DNA and RNA. So we have a bit of a problem there. So we've got a slight chicken and egg situation when it comes to that question. But the thing is this: if we go back to the previous picture, what we have here is we have material coming in which is not able to escape. So over time, the cell is going to fill up with more and more material, so it's naturally going to start getting bigger and bigger and bigger and bigger, and it's going to get to the point where it will naturally split and divide into two smaller cells, and then they will bring in material and they will get bigger and bigger and bigger, then they will eventually split to form new cells and so on. So this process of division is relatively straightforward. It's just a question of volume. Once you achieve, once the volume in here becomes too large, the cell will just naturally divide. Okay? Do you know what? I shouldn't really be using the word cell. I should say the liposome will naturally divide. So that kind of reproduction is, once again, it's rather straightforward. It's very simple, and and it predates the appearance of DNA and RNA. So the importance of DNA and RNA is this: they are essential for the synthesis of more complex proteins. If you want to start making complex molecules, DNA and RNA are very, very important. So recently it's become known that we can actually make small molecules of RNA, and these molecules of RNA can reproduce without enzymes. So through very simple chemical reactions, we can make small pieces of RNA, and these small pieces of RNA can reproduce themselves again and again and again. And these pieces of RNA can be used to make proteins. So essentially these pieces of RNA will keep making the same protein again and again and again. And if that protein is useful, then great, it's going to help the cell. The cell will go forward, and that's evolution moving forward. If, however, the RNA is making a protein that's detrimental to the cell, well, in that case, natural selection is going to kick in. The liposome will essentially break down, and that particular avenue will be gone. So DNA and RNA are important because they make these complex proteins, and they make them faster. So they help to catalyze the rate of protein production. So they are very, very important. There's no denying that. So, as I said, small sections of RNA can be made in the lab under natural conditions. Now remember, these are lab conditions, so they are controlled a lot more than natural conditions would be, but they are approximations of natural conditions. And this would suggest that the formation of RNA through synthesis that is not biologic is possible. Okay, so we can make these small pieces of RNA without biologic processes. We can make them through non-biologic processes. Okay, and so all of a sudden we have very small pieces of RNA. These small pieces of RNA are capable of reproducing themselves, and these pieces of RNA are capable of catalyzing and increasing the rate of protein production. So okay, so now we have a situation where we have the inside of our liposome, we have a nice solid cell wall, we have an interior that's full of lots of different proteins. Some of these molecules are RNA, and these molecules of RNA are taking material that's coming through this bilayer sheet into the interior, and it's taking those monomers and it's combining them together to form complex molecules, some of which will be helpful to the cell. Some might be things like phospholipids, which can be used to make the cell wall bigger, repair the cell wall, and some of them are compounds that might be used, for storage purposes, for instance, making, things like sugars that can store energy, and some of the compounds produced might be compounds which can be used to break down those sugars to release energy. So now all of a sudden you can see we're getting to the point where we're approaching homeostasis. The cell is now, the liposome is now approaching the point where it's kind of able to control its internal chemistry. And we've also already reached the point where, as this liposome gets larger, it will then have to divide. So, okay, if we go back to our conditions here, we are at the point where essentially we're taking nutrients into the liposome, and they're being used to make new materials. These liposomes have the capacity to reproduce, crudely, but they do have the capacity. And the RNA within them has the capacity to replicate itself. And we are also approaching the point where we have homeostasis. So as you can see, we are actually moving very quickly towards a point where we have a very crude living organism that's capable essentially of reproducing itself. So just to give you a quick idea, so this is a molecule of DNA here. So as you know, DNA has the classic double helix shape to it. And so if in order to reproduce DNA, we need to cut it down the middle and split this double helix into two separate strands. Now, in the case of RNA, it's just a single strand, and RNA has these base pairs, okay? And these base pairs essentially represent individual amino acids. So the order in which, so each 3 base pairs represents 1 amino acid. So essentially, depending on the 3 base pairs you have in your group, that will represent an amino acid. And so one amino acid is put in after another, after another, after another, and those amino acids will be combined to produce a specific protein. And once the protein's formed, it will detach itself from the RNA and float away, and then the same protein will be reproduced again. That will float off. The same protein gets reproduced again, that will float off. And so RNA essentially is a factory for producing proteins in large numbers very, very quickly. So RNA becomes very, very important in the formation of early cells. Okay, so do you know what? It has actually been a while since we had a break. I'm really sorry for going so long. So let's pause here. get up, have a walk around, go and get a drink of water, and come back in a couple of minutes, please. Hello again, everyone. So before we go any further, let's just take a second to do today's code word. So today's code word is going to be zircon, as in the mineral. So the earliest organic reproduction may well have involved microspheres and liposomes splitting apart, within which we have these small pieces of RNA that are capable of reproducing themselves and producing more complex proteins and things like lipids. So recent studies have indicated that these small RNA molecules could join together to produce longer chains. That's good. Longer pieces of RNA means we can form even more complex molecules. The more complex the molecule, the more advanced we're becoming. So by adding additional RNA pieces together, essentially you're increasing the functionality of the molecule. So furthermore, studies have also shown that all the building blocks for RNA can be produced through the reaction of proteinoids with common minerals. So once again, the formation of RNA isn't a massive stretch. So the next question is, well, why do we think that things actually started with RNA? Why didn't they start with DNA? So, it's a rather obvious question. So in order to reproduce DNA, you need to use an intermediate step, which is called messenger RNA, or mRNA. So mRNA is important because, as I say, that's what we use to reproduce DNA. So essentially, our ability to reproduce DNA is dependent on RNA. So that means, in all likelihood, RNA had to have come first before DNA. Now, the great thing about RNA is this. RNA is very, very prone to transcription errors. So every time you take an RNA molecule and you copy it to make a new RNA molecule, there are going to be mistakes. And those mistakes are good because, as I said, each one of these base pairs here, so each three of these base pairs here, represent a different amino acid. So if you make a mistake and you change one of the base pairs, that can mean you can have a different amino acid, a new amino acid slotting in. But that means you're creating a new protein. So once again, through blind luck, you are essentially creating a new protein, and that protein could be good, it could be neutral, or it could be detrimental to the liposome. So once again, it's a game of chance, but sometimes it'll work, and most of the time it probably didn't. So this means that during this early stage, we have a range of new proteins being formed, some of which will be neutral, some will be harmful, and some will be helpful. And some of these longer proteins, once we have these long pieces of RNA, well, they will begin to bundle themselves together to form enzymes. And as I'm sure you remember from high school biology, enzymes are essentially catalysts. They help to speed up the rate of biologic reactions. So they'll do things like they'll speed up the rate of proteins being broken down to release energy, or they'll have the capacity to break up waste proteins and break them down into amino acids that can be used to make other things. And so essentially, once you start having things like enzymes, well, once again, you're moving towards homeostasis. This sphere is moving towards a point where it's capable of controlling its own internal chemistry. So you can see by this point, we are remarkably close to having something that we could consider alive. So let's be honest, though. At this point, we have several key steps outlined. And these key steps make sense based on based on experiments and the available materials. So, okay. However, one of the big disagreements is the origin of the monomers and the polymers. So many argue they were sourced from atmospheric compounds, as we discussed. However, some argue that life actually started around hydrothermal vents. So the most important thing is to remember that we just don't have all the answers, and that's what makes discussing early life so complicated, as I'm sure you've just felt over the last few slides, extremely disjointed. It's not a particularly clear picture. So anyway, let's talk about the people that believe that life actually started around hydrothermal vents rather than due to amino acids created by lightning. So to start with, what is a submarine hydrothermal vent? Well, here's a picture of one. Okay, so submarine hydrothermal vents are created when water gets sucked down into the oceanic crust at spreading ridges. As it gets sucked down into the oceanic crust, it gets heated up because the crust in that area is very, very hot because it's new crust. Okay, so that makes the water buoyant. So the cold water gets sucked down into the crust, gets heated up, and because it's buoyant, it naturally rises up and vents out onto the seafloor. Now, as that water is circulating through the crust, it scavenges, it dissolves elements from the rocks that it's passing through. And it will dissolve elements like iron, copper, lead, zinc, and sulfur. And so when this hydrothermal, this hot water, vents out onto the seafloor, it cools down very, very quickly. And so these dissolved metals have to form minerals, because essentially as the water cools down, the capacity of the water to transport these elements dissolved in the water is rapidly decreased. And so these elements have to form minerals, and so they precipitate out of the water as sulfide minerals. So you get iron sulfide, copper sulfide, lead sulfide, and zinc sulfide forming. And they will, over time, they'll build up these structures here, which we refer to as chimneys. So as I say, the elements that are scavenged as the water circulates through the oceanic crust essentially precipitate as sulfide minerals, and when the hot water vents onto the seafloor. So remember, the hot water is going from about 350 Celsius in the rock, and it's suddenly venting into water that has a temperature of somewhere in the region of about, 2 to 60 Celsius. So that's a pretty significant temperature drop. And so that means the water that's venting here has to very quickly deposit the elements that it dissolved as it was passing through the oceanic crust. So as I said, the minerals will build up to form structures which we refer to as chimneys, and these can reach a height of between 40 and 60 meters. So if the sulfide-rich hydrothermal fluid has a black color, like this one here, the chimneys are referred to as black smokers. However, there are different chimneys that have a white color. So these chimneys are venting fluids, hydrothermal fluids, that have a slightly lower temperature, and they contain lots of barium, calcium, and silicon, and that's where the white color comes from. So these are referred to as white smokers. So there's two different types, black smokers and white smokers. So during the Archean, the Earth's interior would have been a lot hotter, and the lithosphere would have been a lot thinner. So that would have meant there would have been lots and lots of submarine hydrothermal vents, and so there would have been, tons of black smokers, tons of white smokers all across the seafloor during the Archean. So to start with, if you believe hydrothermal vents are the best location to start life, there were plenty of opportunities, plenty of locations in which life could have begun. So the other thing is that the hydrothermal fluids which are venting out onto the seafloor contain carbon, hydrogen, oxygen, nitrogen, phosphorus in small quantities, and huge quantities of sulfur. So, all right, we have the basic building blocks for our monomers. We also have heat in large quantities, and this heat provided by the chimneys will help to drive the chemical reaction. So once again, that's another positive. So it's hypothesized that polymerization, taking the monomers and turning them into larger proteins, can take place on the surface of clay minerals near the hydrothermal vents. And these polymers will go to form protocells, a bit like the microspheres. So analysis of these hydrothermal waters has revealed that there are amino acids in them. So we have the amino acids, we have the environments, the clay minerals on which we can take those amino acids and turn them into larger molecules. And these larger molecules have the capacity to form very, very simple cells, a bit like microspheres. So, we have the basics covered. However, it's also been argued that the very hot, very water-rich environment will actually help to inhibit polymerization. The problem is that yes, the hydrothermal fluids may well contain the amino acids, but as soon as that hydrothermal fluid is essentially released into the ocean, it gets very, very rapidly diluted, and the amino acids are essentially washed away and lost. And so that will be a major problem, and that will probably inhibit the polymerization of the amino acids to make larger molecules. So that's a very serious problem. So it's uncertain whether hydrothermal vents actually offer a suitable location for life to begin. However, if they do, then that obviously has major implications for life in the solar system. So we've actually realized that quite a few of the satellites, the moons that orbit other planets, actually have layers of ice on their surface. So, got planets like Europa and Ganymede, Titan, even the dwarf planet Pluto have layers of ice. And what we've realized is that where this layer of ice is in contact with the rocky portion of the moon, well, as long as this rocky portion has some degree of heat, it will melt the ice, creating a layer of liquid water. Now, if this liquid water gets pulled down into the rocky portion of the planet, where the water can come in contact with the rock and scavenge metals, well, when that water vents back out into these oceans beneath the ice, well, it will form black smokers and white smokers, and therefore that gives us the possibility that you could have life around them. And so, dwarf planets like Eris and Pluto, and moons like Triton, which appear to have, large, thick ice sheets with layers of water in contact directly with the rock below, well, they provide very, very good environments in which we could, in theory, have black and white smokers, which would provide the basic environmental setup for life to begin. And so people have suggested that, these satellites, these dwarf planets, actually represent a very good possibility for the formation of simple life. And so, space agencies like NASA and the European Space Agency have been thinking about ways of trying to get to one of these bodies, drill through the ice to sample the water underneath and to see what's actually going on. In the case of Ganymede, we're actually quite lucky in that the ice has lots of cracks in it, and so some of the water underneath actually vents out into space. And so I think it's NASA have been trying to come up with a spacecraft that's capable of flying through these jets of water and sampling them to see what the chemistry is like, to see whether there's any indications that there may be organisms living in the water. So, if life could begin around black and white smokers, it would be very, very important for life in our solar system and maybe life in the universe as a whole. So, in all probability, it's actually more likely that life around submarine and hydrothermal vents actually migrated into those environments and didn't form in those environments. What can't be denied, though, is that the hydrothermal vent environments do provide essentially islands of biodiversity in a otherwise pretty barren abyssal plain. So, the ocean floor around the hydrothermal vent is pretty, devoid of life. However, the hydrothermal vents themselves are absolutely stuffed with organisms. So, they are a great place for life to live once it's formed. So, next we need to think about what's the Earth's oldest organism. So the earliest form of life would have been a prokaryotic cell. So that's essentially a cell that has a cell membrane made of phospholipids, and within the cell membrane you have the interior that contains essentially all the that contains the materials, and it also contains the cell's DNA or RNA. Essentially, this is what we've pretty much ended up with after having worked our way through all these, non-biogenic reactions. We eventually could end up with something like this. A very simple version, granted, but something like this. So these prokaryotic cells do not have a membrane-bound nucleus. So the DNA, the RNA, is not in a nice confined space like this cell over here. It's just floating around loosely inside the cell. So that's what makes this one a prokaryotic cell. The DNA, the RNA, is not in a nucleus. In the case of a eukaryotic cell, like the cells that make up our body, the DNA is contained within a nice nucleus. So it's nice and tidily stored within the cell's nucleus. So the first single-celled life was probably a type of prokaryotic cell called an archaea. And they look like bacteria, but they are chemically and genetically different. Plus, they can survive in very hot, very acid, and very saline conditions that would kill your normal bacteria. So this suggests that they are very likely the first type of organism. They're the simplest, and they can survive the most adverse conditions. And life on the early Earth would have to be able to have survived very, very adverse conditions. So, this makes quite a lot of sense. So many archaea are classified as extremophiles. These are organisms that can survive very, very extreme conditions. So very, very hot environments, very, very acid environments, very, very saline environments. So although no direct fossils of Archaea are present in Precambrian rocks, some paleontologists believe that there are indicators of their existence. And so we've already touched on this already. So there's a layer of graphite within the Ishura Greenstone belt. So remember, the Ishura Greenstone belt dates to 3.8 billion years ago. And this layer of graphite has a carbon-12 anomaly, and it's positive. So if you were to look at our bodies, or the body of a a tree outside your house, it would naturally have a positive carbon-12 anomaly. That's an indicator of biogenic origin for that carbon. So the fact that you have these positive carbon-12 anomalies in this layer of graphite suggests that the carbon that makes up that layer of graphite probably came from an organic source, which suggests life. It also suggests that whatever that organic source was, it was photosynthesizing. So that's very, very important. Now there is a caveat though. This layer of graphite formed 3.8 billion years ago. A lot of stuff has happened to it in between. So can we be certain that the carbon-12 anomaly that we measure in that layer of graphite actually reflects the material that went to form that graphite? The answer is no. We can't be sure. So we have to be honest about that and say that yes, the data is interesting and supports the idea that it may have been formed from organic material, but there are numerous and difficult questions that cannot be answered. So does this really work? It's very debatable. I would personally err on the side of caution and say I wouldn't trust it, but there are some people that feel it's strong evidence. So in the early 1900s, a gentleman called Charles Walcott described layered mound-like structures in the 1.9 billion year old Gunflint Chert from Ontario, Canada. So the Gunflint Chert is actually Paleoproterozoic, so it's not Archean, it's actually younger. But he did spot these layered mounds. You can see this is a piece of the kind of material he would have seen. You can see it's got this very, very distinctly lumpy, it's got distinct lumpy look to it. Where these lumps are split open, you can see they've got lots of concentric banding, a little bit like a jawbreaker. And you can see, if you look at them in plan view, when you take a slice through them, you can see they have layer on top of layer on top of layer. You can kind of see it quite nicely in this side right here. So what he proposed was that these structures represented reefs constructed by layers of algae, one layer on top of another on top of another, and these are called stromatolites. Now, this hypothesis of Walcott's wasn't actually proven until the 1950s, but nevertheless it has been proven. He's been proven to be correct, and yes, these structures are what we refer to as stromatolites, and they are indicators of very early life. So these are essentially structures that are built by early life. We don't actually have the fossils of the organisms that were building them, but we have the structures they left behind, these stromatolites. So that tells us that we had these sheets of photosynthesizing blue-green algae forming these mounds. So the sheets are formed when sediment gets stuck to layers of photosynthesizing blue-green algae. So in order to protect themselves, the blue-green algae naturally exude a layer of slime onto their surface, and material will just build up on top of that layer of slime. And so slowly, as material builds up, essentially it will seal in that layer of blue-green algae, and then a new layer will form over the top. So we actually have examples of stromatolites even now. So these modern stromatolites live in extremely salty environments where snails that would eat the cyanobacteria under normal conditions cannot survive. So we actually have modern equivalents. So we can see how they're forming, how these stromatolites form in the modern environment. So the oldest undisputed stromatolite is from South Africa, and it dates to 3 billion years old. However, possible older examples occur in the 3.5 billion year old Warrawana group from Australia and the Glacier National Park in Montana, although these stromatolites are disputed by some. So we have solid evidence for life 3 billion years ago, and we have good evidence for life 3.5 billion years ago. So we need to remember that there would have been individual cells before stromatolites, but those individual cells did not fossilize, so we cannot be sure when they appeared, which is a very important thing to remember. So just so you can see, just going to get rid of these. So these are the stromatolites in the Warwana group. You can see we have this lumpy appearance, and when the stromatolites are split open, you can see they have a distinct concentric appearance, and you can see on the side here, you can see layer after layer after layer. So they look very stromatolite-like. And these are the stromatolites from Glacier National Park. You can see each one of these is an individual stromatolite. So each one of these, column-like structures represents an individual stromatolite with one layer on top of another, on top of another, on top of another, on top of another. So they look a lot like stromatolites. And from what we can tell, they were forming in the correct type of environment for stromatolites: shallow, warm, marine environments. So there's a very good chance that they were formed by blue-green algae, and these, as I say, date to around 3.5 billion years ago. So these are modern stromatolites. This is Shark Bay in Australia. And so you can see they form this mound-like morphology, which is remarkably similar to the mounds that we see in stromatolite fossils, should I say. And when we cut open these stromatolite columns, we see that they contain, if we cut them open across the top, we see nice concentric banding. And if we were to cut them open lengthways, we'd see lots and lots of concentric banding layers, one on top of another. And so essentially these modern stromatolites show very nicely the structures that we see in these ancient stromatolites. So there's a pretty decent body of evidence to suggest that these features are formed by photosynthesizing blue-green algae, just like modern stromatolites. Once again, principal uniformitarianism. If it's happening now, it's happened the same way in the past. So when did life appear? So let's just go back over this one more time. Well, if we believe the graphite layers are in the 3.8 billion year old Ishura Greenstone belt, and if we believe they were produced by photosynthesizing algae, then we must assume the first cells appeared sometime around 3.8 billion years ago. An important point to note about that is that if these cells were photosynthesizing, then that means they have to have had chloroplasts. Those are the structures inside cells that allow photosynthesis to happen. And that's important because that means that chloroplasts were actually added quite late in cell development. So it means there would have been more primitive cells before those photosynthesizing cells. So that's a key point. So that would mean that life would actually be even older than 3.8 billion years. So these very, very early bacteria, very, very early single-celled organisms, would likely have not needed oxygen to respire, so they would have been classified as anaerobic organisms. And they would have been completely dependent on external sources of nutrients. They're what we refer to as heterotrophs, like us. We can't manufacture our own nutrients, so we have to ingest them by eating plants and other animals. Now, plants, on the other hand, are autotrophs. They have the capacity to make their own nutrients, their own food. So these early bacteria would have been heterotrophic. They would have taken material in and used it to make molecules, used it to make protein, should I say. So they will also have been prokaryotic, so no nucleus. And the probable food source for these very early bacteria was probably something referred to as ATP, which acts as an energy source for reactions. It's actually the stuff that's used in our cells as an energy source as well. So ATP is quite important. And ATP can be made relatively easily, naturally, from simple gases and phosphate, so it's very likely that ATP would actually have been available, just as through natural reactions, in the environment at that time. So it was there, easily found, easy to use. However, the problem is that the supply of ATP would probably have been very quickly exhausted, as the number of prokaryotic cells increased. So at this point, cells would have had to have produced come up with a new way of producing energy, and the simplest way of doing that is through fermentation. So in fermentation, you take a sugar, like glucose, and you split that sugar, releasing carbon dioxide, alcohol, and energy. So sugars like glucose and sucrose are relatively simple, and would not have been difficult to make, especially if you have pieces of RNA to really help to speed up the process. And interestingly, most prokaryotic cells actually still use fermentation as their source of energy, because if it ain't broke, don't fix it. It works perfectly for them, so why try something different? So once we had cells, things will tick along until between about 3.5 and 3 billion years ago, where we know we definitely have chloroplasts becoming incorporated into prokaryotic cells. At that point, those cells can begin to photosynthesize and produce their own nutrients. Okay, everyone, good work. I appreciate that was a very long presentation, and got to be honest, it wasn't one of my greatest ones. It was, a bit jumpy, but you did very well sticking with it. Don't forget, the code word for this presentation is zircon. I repeat, zircon. So keep an eye out for the next presentation, and take care.